Okay, this is section 5.5 for college algebra. And in this section, we're going to be looking at functions that represent exponential modeling. I want to point out some themes in this section that are going to be common to every problem that you work. And that will be the layout of where things go in this exponential model. First of all, this right here will always be the final size of the population, what it grows into, or what it decays down to, because sometimes what we call the growth factor, which is this decimal here, sometimes it'll be positive, and then we say that the population grows, and sometimes this growth rate will be negative, and so we say that it actually decays. Okay, so what you are seeing on the left-hand side of the equal sign is the final size of the population, whereas what you're seeing right here, always directly to the right of the equal sign, that will be the initial size of the population. In other words, what the population began at when this population went under observation. Okay, so that's what that number stands for. Then what you're seeing right here, that is called the growth rate. And we give it this name when that number is positive. We call it a decay rate when the population goes from a certain size to an even smaller size. Then we call it a decay rate. And that's when this decimal is negative. Okay, and then the TUC, that's the amount of time. That time can be in minutes, years, etc. Okay, so we are using this function right here. I just wanted to explain the bits and pieces of it to you and what they stand for. And we're going to now begin to drag in this information to answer the question. So it says population of Stewart can be modeled by the following function, where T is the number of years since 2020. So basically what they're telling you is that 2020 is when they began watching or observing this population. Use the above function to answer the following question. What was the population of Stewart in 2020? So they're basically just asking you what was the initial population, because this year matches this, so this is right at the moment when they started observing it. So they're really just talking about the initial population. Therefore, for this particular answer, you really don't have any work to do. I mean, some students will say, well, 0 years have passed between here and here, so I'm going to put in 0 for the amount of time that has transpired since they've been watching it. In for T, you always put how long have they been watching the population. Well, since these years match, 0 years. But if you put a 0 in there, you're going to have e to the 0, which is 1. 1 times 16,648 is 16,648. So just a quick way to do that is, remember that I told you this number directly to the right, but before the E is the initial population. So you really had that answer without doing anything. Okay, then it says, in what year is the population of Stewart projected to reach 22,641? So in what year? You're going to have to figure out how many years it takes it to get this big, and then you're going to have to add that to 2020 when it began, because of the wording right here, in what year. If this had said, how many years does it take the population to reach 22,641, then you would just give whatever you get for T. But when they say in what year, you have to consider what year it started in, and then add whatever you get for T. So let's get at that. I'm going to write the equation above, and let's see. We want this to be our final population. I'm just going to abbreviate that. And we're going to put that in for y. Remember I said that, or for p. Remember I said that this number is the final population. So we are going to put that in right there, 22,641. All I'm doing is plugging into this equation right here. This is a constant, the initial population, whatever you were told that it is, it continues to be that, no matter what other numbers you're plugging in. 16,648, and then it's E raised up to a growth rate, which they gave you. Most of the time you're finding that yourself. 01279. And what we're doing here is, since we're asking what years, we have to know how many, first of all, how many years did it take for it to get this big when it started at 16,648? So we need techniques for solving exponential equations. And this is where previous sections come in. In sections 5.3 and 5.4, mostly in 5.4, you were learning how to solve exponential equations using logs. The particular kind of log I'm going to use is natural log, and that's only because this base is e. But before you go taking the log of each side so that you can knock this exponent down on base level, you're going to want to make this exponential expression stand alone. In other words, no multiplier. So we're going to divide off this coefficient, this multiplier, and whatever we do to one side, we have to do to the other side. So this will be gone, and all you'll have left is e to the 0.001279. You don't have to write that leading zero as you're going through the calculations. When you report an answer, if it has a leading zero, yes, write it. But as you're going through the calculations, you can just drop it. Okay, we are trying to solve for t, and right now I want to go put in my calculator and get a value for 22,641 divided by 16,648. So we're going to get here, clear. Okay, so 22,641 divided by 16,648. And I get 1.3599. I'm not going to round it off. I'm just going to indicate myself so I can clearly think about what the next step is. That I did for this fraction get a decimal that ran on and on. So I'm going to put these three little dots. Okay, then let's get at getting this out of the air and back down to ground level. So when you want to take your variable out of the exponential position, you take the log of each side. Just like you did in 5.4. And you have to understand that for natural log, the base is e, and then one of the most often used simplification methods for simplification with logs is the inverse property, and that property says when the argument is equal to the base, they cancel, they take the log with it, and down comes the exponent. So instead of being it up in the exponential position, you now have it as just a multiplier. It's not an exponent anymore. This is what allows you to bring it down. Okay, and then here, well, that would be a matter for the calculator. So even though I wrote it like this, I really have the exact number that I got without any numbers being missing. You need to keep those numbers in your calculator window and just keep working on them, because otherwise you'll lose accuracy and the final answer gets marked wrong. So I want to know what the ln of this is. So I'm going to push ln. Then I want to paste this entire number without taking any of these numbers off right in here. So to paste a number from the previous line, you press second. And let me move this up. You're going to press second and answer. Answer is this button next to the enter key that says ANS. Don't forget it's a second function because it's in a different color. So Press that color, then press that key, and that means it took this and pasted it in there, every last number of it. So now the ln is 0.307. Again, it runs on with a bunch of numbers after the decimal. You need to keep them all, so do not delete each time. You want to keep these numbers running on your screen, the true and accurate version of these numbers. Now you can write down a few numbers just so you can concentrate on what you're going to do next. That helps with that, and that it runs on, and that you do actually have that still in your calculator window. So now when I look at this, I say, okay, I'm trying to solve for t. There's a multiplier next to it, so I want to divide that multiplier right off the t so that the t is solved for, so that it's isolated. Okay, so all of this cancels with all of that, leaving you with just t. This number right here, 3074, that runs on. I actually still have the entire thing right here in my calculator window, and I'm dividing by 0.001279. And I get 240. They said we could round this to the nearest year, the nearest whole number. So I'm going to say that that is closest to 240 years, because this is the nearest whole number and that number is not big enough to bump it up. Okay, so we are this many years into the future. However, as stated, they say in what year. They're actually asking in what year, 2016, 2018, 2030, like that. This is just how many years. So you go and take when they started observing this population, which was 2020. That was the first time they observed it. And then 240 years down the road, it has grown into this 22,641. So what year does this happen in? Just add these two. Be 22. This 40 gets added to the 20. So in the year 2260, at that point, the population would have grown to 22,641. Okay? Now, in this problem, they made it a little easier than the rest of the problems by giving you this growth rate. Most of the time, you're going to be finding that so that you can just begin the problem. We're going to see that happening right away in example 2. So here we get to example 2. You have, once again, a growth model function where this is the final amount. Just going to abbreviate. This is the initial amount. This is that decimal growth rate, and t is time. Okay, those two things are obvious. K is the growth rate. Okay, so it says, according to a 2010 U.S. Census, that tells you when they began observing this population. Okay, at that point in 2010, the initial population of Okeechobee was 5,489. Then 10 years later, in 2020, so that already tells us we're going to be putting in 10 for time in this little exponential function. Because we started 2010, now we're talking 10 years down the road. We found that the population had now grown to 6,467. So this right here would be the final population. That's your y value. This would be the y sub 0. They often call the initial amount just the variable that's being used over here, but with a little sub-0, a subscript of 0. And so we have a lot of things to plug in here besides the fact that from here to here, 10 years have transpired. Okay, so now I'm going to start working with this growth model. It says the exponential growth function that models the population of Okeechobee would be this. Okay, final population. Let's see, where t is a number to write an exponential growth function for the city round this to 4 significant figures. Okay, so here I go. This is the initial population, final population. So I'm looking at this as I go and plug in, and my little note to you that the final population, which is 6467, goes right there on the left side. My initial population, which is what the population was when they began observing this population. And then right next to it, according to this equation, would be E. We do not know K right now, but we do know that we're observing this population 10 years. And so I put a 10 in for T, 10 years from when they began observing it. Now it just gets into a matter of trying to isolate the E term, in other words, getting this multiplier off so that we can take the log of both sides. And again, it's because your variable is in the exponential position, in the power position. The only way you can knock it down to base level is to take the log of both sides. So first, before you take the log of both sides, you're going to divide off the coefficient of the E term. You want to get that E term as clean as possible before taking the log of both sides. So here, this is gone. Here, you're going to get some kind of decimal, and we're going to leave the entire decimal in the calculator. But I'll put I'll write a few digits just again so we can figure out what our next move is. So it's 6467 divided by 5489, and that is 1.178. 1.178. It goes on, and I am keeping that full number in my calculator. So this is what I got from this fraction. The 5489 is gone, so on the right side of the equal sign, we just have E to the 10k, raised up to a power of 10k. At that point is when you're going to go in and take the log of both sides so that the variable you're solving for is no longer in the exponential position. So I'm going to take the ln of that big long number in my calculator, and that would force me to take the ln of this side. But as stated in the first problem, one of the most used properties of logs that is used in solving these equations is the inverse property, and that's what's happening on the right side of this equation. When this argument matches the base, they go out, they take the log with it, and down drops the exponent. ln of this, you're going to put it in your calculator, so it's a good thing you still have that exact version of 1.178. So now you're going to take the natural log. You want to paste this exact number right in here, so you press second answer as I did in the first problem. So second key, answer's down here, and you'll see that it has dumped the answer from the last line. Close up the parenthesis. That is the ln of 1.178. So now we have on this side 0.163, and it just goes on and on and on. But by writing part of it, that gives you a good sense of where you're going next. I just messed up a little bit, but I can just enter it again. So anyway, what you're doing at this point is dividing both sides by 10 so that you will ultimately have that growth factor. Now, I accidentally pressed the key here, so it typed in something weird. So this is the number that I was getting at, the 0.163966. I'm just going to have to type it again. Otherwise, I would have pressed second answer. Okay, I'm trying to do 163 number with all the decimals after it divided by 10. 2329, and I'm dividing by 10. Let me make sure I copied it right. 163,966, 2329 divided by 10, and it is 0.01. Okay, so I'll finish it up here. Your growth factor is equal to, And I believe they said that we would do the growth constant to 4 significant figures. So let's see, what do I have here? 0.01639. Okay, so let's see, 4 significant digits. So this would be the 4th digit after the decimal, and the number right next to it is strong enough to bump it up, so it's going to be 0.0164. 0164 after the decimal. Okay, then it says use the population growth model to predict the population of Okeechobee in 2030. So again, the observation of this population began in 2010. So you want to count from 2010 to 2030, and as you can see, it's 23 years down the road. Now, I know you can do some things in your head. I'm just trying to be very specific for those that need every step in order to learn. So use the population growth of Okeechobee in the year 2030. Round the solution to the nearest whole number. Okay, so I got my 20 years. Now I'm going to go right back to my equation up here. Y is equal to initial times e to the kt. I now know k, and I'm going to plug in how long this is going to take. Okay, my prediction 2000 predicts that the population will be, so I'm going to do some work right here. Okay, that's the beginning of that. Initial amount never changes. It's 5489. Okay, and then it is, so that's the y sub 0, and then it's e to a power of k times t. E to a power of k, which we're using 0.0164. 0.0164, and we're multiplying that by 20 because we're looking at the situation 20 years down the road. So that I'm putting that in for t. Again, just plugging in right here, following this. Okay, so then all you're going to do in order to get this final answer, how big the population is 20 years down the road, is just put it in just like this. I'm going to clear what I have here. So it's 5489 times, call up the e term on your calculator. So that's a second function. So I'm going to press second, and then right down here, you're going to see the e to the x right in this first column. Whoops. Okay, so 5489 times e raised up to a power, and the power consists of the 0.0164 times 20. 0.0164 times 20. Both of those things are in the power. So you get multiply them together, close that parenthesis so that it'll do this multiplication first, then it'll go e raised to that power, then it'll multiply by 5,489, just order of operations. So as you see, what you get here is that 20 years down the road, the population has grown from 5489 to 7,620. That 9 gets bumped up to be 20, that 19, and that's because of the 7 right next to it, because we're rounded to the nearest whole number. So this is going to be approximately 7,020 people rounded to the nearest whole number. Okay, and that was stated right there, that they wanted the population 20 years down the road, nearest whole number. Okay, so here's another answer right here. Determine the year when the model predicts the population to be 10,978. Again, determine the year. They're not saying how many years, although that's a precursor to being able to answer this question. If you're going to determine the year in which this is happening, you have to find out first how many years have transpired. In other words, you're solving for t. Okay, so let me straighten this up, and let's go in for this. Okay, once again, you're looking at this function right here, final amount, initial amount, growth factor, and then we are solving for t. When they say determine the year, you must find this first. Okay, so in for the final amount, I'm going to put this. The population has grown into 10,978. The initial amount will be directly to the right. That y sub 0 is 5489. And then it's e to the growth factor that we're using, which was the very first thing that we found, the 0.01. And I'll label this for you that this represents the growth rate. It's how fast it's growing, the population. So it's 0.0164, 0.0164, and we are solving for t. So we don't have anything to plug in for t if that's what we're solving for. Again, I'm going to go at this problem by isolating this e term. In other words, get rid of this multiplier in front of e so that I can go in and take the natural log of both sides. Okay, so this is gone. We're talking about having e to the 0.0164 t. And then over here, we're going to get a number that represents 10,978 divided by 5489. 10,978 divided by 5489, and that turns out to be exactly 2. Now let's see, wait, what did I just do here? Let me make sure I put this in right. 10,000, oh no, wait. Yeah, so that was, okay. Get my head on straight. So I got rid of that. Press this in. I make sure I got the right numbers. 10,978 divided by 5489. So I can replace all of this with 2, and then we're going to keep going. Remember, we're trying to solve t. Therefore, our t cannot be in the exponential position. We've got to bring it down. So we bring it down like this. Take the natural log of this side, which forces you to take the natural log of that side because you always have to do the same thing to both sides of an equation when solving. Here you can see the e's cancel, take the log with it, and down comes the exponent to base level where you can then just solve for t. This, we're going to have to get this from the calculator. So it is ln of 2, and we get 0.69314, and it goes on and on and on. We have one more step. We have to divide this multiplier right off of the t. Likewise on the other side, 0.0164. So t is approximately, and again, it says round to the nearest whole number for the part that we're on. So this turns out to be divided by 0.0164, approximately 42 years. If I'm rounding to the whole number, this is the whole numbers place. That number's not strong enough to bump it up, so we're talking approximately 42 years. But then to answer this kind of question with this kind of wording, in what year means you have to consider when they started observing this population, which was in 2010, and add the 42 years that it has taken for it to reach this, to get this big, for the population to get that big, 10,978. So in the year 2052, that's the year at which it reaches this size. Okay, so that's that. Okay, moving on to number 3. Lots lots of parts. It's tiring to even speak it. Okay, so then let's see what we got for number 3. Okay, so Escherichia coli, commonly referred to as E. coli, is essential for modern biotechnology research. One reason for this is the ease and speed at which it can be cultivated. In other words, the ease in which you can grow it. Under ideal laboratory conditions, when this bacterium is grown in a nutrient broth medium, the number of cells doubles every 21 minutes. Okay, so when they start talking about doubling, they're just saying the point at which the final population becomes double what it started. So you can start this problem off by recognizing that they have just said the culture doubles in 21 minutes. So that's giving us quite a bit of information that we can begin plugging in right here. Okay, so we're looking at when the population doubles. Remember, in all these problems, if you do not have the K value, you're starting off trying to find that so that you can answer the rest of the parts of the problem. Okay, so we're going to say that the final population, this Y, is double the initial population. What's double the initial population? 2 times Y sub 0. I'm going to put that right here in place of this Y. So take the initial population and double it, and that's the population at which we are right now after 21 minutes. So we're going to leave the Y sub 0 there. That's the initial population. E to the, don't know what K is, but we do know that we're talking 21 minutes into the observation. Now, there is a shortcut here that when they say population is doubling, you can just go right to what I'm going to do next. Like what I'm doing, and you can go right to this step, what it looks like after I do this. You want to get that multiplier off the E so that you can solve for K. So I divided off that multiplier likewise here, and you see that you jump right into what the word double means. So you're going to have a 2 on this side, and you're going to have a E to the 21K on the other side. Okay, sort of move that over a little bit. And now we're trying to solve for K so that we can use this K value to solve other parts of the problem. So I'm going to take the ln of this side so I can knock that K down to ground level, and I'm going to also have to take the natural log of the numeric side. Okay, so I had just gotten this value a minute ago. Ln of 2 is this 0.693, but I want to keep the values so that I can pull them down in each successive step. So I'll just press it in again. So ln of 2, there it is right there. I'll write something that represents it, but I'm still holding the whole number in the calculator window. Over on the right side of this equation, lower this a little bit, don't have much room here. This E cancels with this, that goes down, and you have 21K. So almost have my K value. I'm just going to divide this by 21 and this by 21. Okay, so right away, that gives me a K value. And once again, let's see what it says here about K. That we should go to 4 significant digits. 4 significant digits. Okay. So I had ln of 2 in there. That was already there. That's where this 0.6931 came from, ln of 2, and then I'm dividing both sides by 21. And I get 0.0330, runs on and on and on. But they say to 4 significant digits, something that's kind of weird about this section is that when you're doing significant digits, a zero that happens after a decimal really doesn't count as a significant digit. Yet in the last problem, when it asked for 4 significant digits, so that's something kind of a little inconsistent just because you have different people writing these questions and the answers to them. They asked for 4 significant digits here, but I only kept 3 because really only the 1, the 6, and the 4 are considered significant digits. Because when I did keep an actual 4 significant digits, which would have meant keeping the next number because that one doesn't count, I only got 700 and I got 7,618. And on the answer key, it's 7,620, so that's kind of annoying. This is actually what 4 significant digits is. Okay, so I was at the point where I was going 0.6931 divided by 21, and I got 0.033. 0.03301. Okay, and if you're looking at that right here, this doesn't count. I need 4 significant digits. So it's 1, 2, 3, 4. That number right there. 1, 2, 3, 4. And I'm going to stop right there. I'm keeping 5 of these numbers only because that one really doesn't count as a significant digit. So just these 1, 2, 3, 4. That 0 has to go up to a 1 since I'm truncating that decimal right at that number. I look to the neighbor next to it, so it's 0.03301. Okay, that's going to be my K value that I use throughout the rest of the problem. Okay, 0.03301. Okay, next. Okay, approximately. Okay, and so if you want to rewrite this function with the new K value, it would look like this. That would be the answer to this question because they like to ask several questions. This will be for whatever the final amount grows into, and they can change that to whatever they want in each question. The initial amount never changes. So we just write y sub 0 again. Now we don't yet know what that initial amount is, so we're just using a variable for it. And this rate of growth never changes either. So this is 0.03301 times d. So all I'm doing is rewriting this function, this growth rate function, but with the growth rate. Okay, now we can go on to answer this next question. Approximately how many bacteria will be present in the colony after 145 minutes? And in this particular problem, which it says at the beginning, the unit for time is in minutes. Okay, so we're going to go approximately how many bacteria, okay, I have to round the answer to the nearest whole number. Okay, so approximately how many will be present after 145? They want to know what is the final amount of bacteria after 145 minutes. Okay, so 4 significant digits. And let's see, somewhere in here, I believe there's one other number, and I should have put that in when I rewrote this. This is what the initial number of bacteria were. So I really could have written this in a better way, which I have to actually because then we have too many unknowns when I go to answer this question. So put that initial amount that they gave you. And then in this previous part, I was busy trying to find the growth rate, which I have. So that's a better version of this function. And now we're going to put 145 in for time. Okay, you'll know from the units after the number where you're supposed to plug certain numbers. So now we're going to go, what is the final amount if it starts off at 450? And we come in here and we go point, so like this whole thing, 0.03301 times t. 0.03301 times t. Okay, so we're just going to straight up put in the 145, which I could have done it the first time I wrote it, but I didn't. So 0.03301, and then you plug in the 145 minutes, and that's just a straight calculation. You're not going to be trying to isolate anything or taking logs, because everything you need to get this final population is over here on the right, so you're simply just putting all of that in the calculator. Okay, so here we go. Clear out. It's 450 times e raised up to a power times second function e raised up to a power, and that power consists of 0.03301 times 145. 0.03301 times 145. And that comes out to be 53943.775. I'm going to keep that whole thing in there. And let me see what it says to round off to. So I'll just do that right here. Process on. Okay, round off to the nearest whole number. Okay, so this 3 is in the whole number position. Look next to it to decide whether to bump that 3 up or leave it as is. So this turns out to be 53944, because we're going to bump that up to a 4. Okay, so that's what happens to the population. It grows to that extent after 145 minutes. Okay, so that is the answer to this one right here. Next question. Determine how long it will take for the bacteria, and for you guys it'll pop up one question at a time. It's just that I have the printed version of this, what's in your homework. Determine how long it will take for the bacteria colony to reach, wow, all of that, round the solution to the nearest whole number. Okay, so I'm going to need some room to do this. Do my calculation right here. So we want to know, when is it going to reach this level? That means it's the final amount. Oops, and I'm writing initial. It's the final amount, so that's y. Okay, again, I'll just be looking at this equation right here, where the y is the final amount. I'm going to copy in 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 billion. And then I'll look at the equation again. I'll refer to it that there was an initial amount, and they gave that in some of the reading up here, 450. That was the initial amount. That initial amount never changes. All that can change is what it grows into. Or if it was a decay problem, what it decays down to. And it will be e raised up to a power that consists of k times t. Yeah, and since we're looking for how long, that means we're solving for t. Okay, so the k value that we found back here was 0.03301, and then times t, which is what we're solving for. So again, you're going to go after this just as we've gone after the last couple of problems in all their various parts. We're going to divide off this coefficient into both sides. Okay, so this is going to be, let's clear this screen, this will obviously be gone. So we got 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. Count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we are dividing by 45. Okay, so we have this number from the calculator, 222, blah, blah, blah. The whole thing is still right there in the window. And then over on this side, we no longer have the 450. Oh, I made a mistake. Sorry about that. I divided this side by 45. It should have been 450. Glad I caught it before I went to the end. Okay. All right. Gotta put that in again. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm dividing by 450. It just has less 2's in it, so I guess I could have kept this. Blah, blah, blah. This is gone, and it's e to the 0.03301 times t. And you're going to solve for t by first getting it down to ground level. That's accomplished, as you've seen in many problems already, even though we're only on problem 3. Is you take the natural log, and that brings this exponent down to this level, where you could actually just divide away that coefficient of t. And if you're going to take the ln of that side, you have to take the ln of this 22222 number, okay, which I got from this 10 billion divided by 450. Okay, and so then we're going to go ln, and I'm going to dump that number in here. So second answer, close it up, and I get 16.916. It's just an abbreviated version of it, 16.916, but in actuality in the calculator it shows a lot more numbers. So this is just to get your head wrapped around what to do next. That's why you write out these numbers in their abbreviated form. But yet you're still holding the entire thing in your calculator window. Cancel, cancel, T. And now this 16.91 number, we still got it sitting right here, and we're going to divide by 0.03301, and we get 512. Let's see, what are we rounding? How long? Determine how long. Now that doesn't say in what year. It says how many years or minutes, whatever the unit of time is. And this one's actually in minutes, as it's said in the very first paragraph. When it starts talking in minutes, all the answers that have to do with time are in minutes. So we're talking 500. They wanted us to round this to the nearest whole number, as it says right here. So this is closest in whole number form to 512. That's not strong enough to bump it up. And then we're talking minutes here. Okay, so that is the last answer for number 3. Okay, so I'm going to do this next one, and then I'm going to stop this video. And then in the other video, I'm going to make another short video where I'll cover 5, 6, and 7. I need to take a little breaks, too much talking here. Okay, so here we go with number 4. It says, again, the doubling period. We got exposed to this in a previous problem. And they're actually letting you write your own equation now. So just go back to the one that you have seen in previous problems. Final amount, initial amount, and then E raised up to a power that's made out of a product, K times T. So you can just refer to that as you answer these questions. So the very first thing they're trying to get you to do is they're describing the doubling period. So this is how long it takes for the final population to be double the initial population. So when the final is twice as big as this, which would be written like this. This final population is 2 times the original population. The y sub 0, initial population, and we're talking about E raised up to a power of K times T, which is that 32, and thus they have given you a way to find the growth factor. So you know the whole deal here, divide by y sub 0, divide by y sub 0. And when you see something about doubling, you could go directly to the part where you have a 2 on this side and an e raised up to a power. So if you already see that that's what's happening, which it is, you could just start right here. 2 on the left side, and on this side we just have e raised up to a power of 32k. And then to get this exponent out of the air, I'm going to take the log, as you've seen me do in all the previous problems. The base cancels with the argument, takes that with it, and you have 32k. ln of 2, we just had that a minute ago, but I'll press it in again. ln of 2 is this right here. And you can write that just as, you know, some guidance of what you're going to do next. 693, blah, 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 goes on and on. You're trying to solve for k so that you can finish this problem. So you've got to divide off that 32. You have to isolate the k. Okay, so this cancels, and you're right here that the k value is equal to, and it says determine the initial population. Okay, so we're getting this k value. Okay, so let's go ahead and put this in. So the 0.693 divided by the 32. And I got 0.02166608. But it really goes on and on and on, and I'm going to keep this whole thing even though I'm only writing this abbreviated version. That really runs on and on and on, and when I write those 3 dots, it means that I have the exact version still in my calculator window. Okay, so now just from reading this first sentence, I was able to find the k value. All I did was plug in that 32, and I looked at this comment about the final amount doubling. That's it. Got the k value, and then once I have this k value, I can finally answer this question. After 50 minutes, the colony's population has grown to 19,998. So this is what you have as your exponential model so far. Y is equal to, and let's see, you have your initial amount here, and then we have E. We now know the k value. That 32 was only so we could find the k value. So you're going to leave time as t, but you're going to put this in for the k value. So let's see. And I'm going to use the whole thing because that could destroy the accuracy. So in my calculator window, I don't just have this. I have 0.0216608,494 times t. Okay, so now this question addresses after 50 minutes. So we're giving the answer to the question in this second sentence right here. After 50 minutes. What is happening after 50 minutes? I don't know, they told you after 50 minutes the bacteria, the colony's population has grown. So they're actually telling you what's happening in 50 minutes. The population has grown to 19,998. So you put that as the final amount of the population. Okay, so that represents that. And then the question is, what is the initial population? Okay, so let's see what we have now here. So after 50 minutes, okay, I got to put the 50 in for the t. I don't have information about this because I'm solving for it. And this will be e to a power of 0.0216608494 times the 50 minutes. Okay. So now we're going to get the initial population by solving for y sub 0. So this is going to be y sub 0. Let's just get a decimal instead of having these two multipliers right here. So it's going to be e raised to a power of this times this. Second function, e to a power. And we're putting that big long number, 0.0216608,494. 608,494. 494 times 50. Okay, I'm taking e and raising it to this power, which is really a product. So I just typed all that in. Okay, there's a big long number times 50, and e is being raised to that power. This is what it comes out to be. So all of this has a power, and e is being raised to the power is 2.953, but it actually runs on and on and on. But now this is a multiplier instead of having a base and an exponent. This is just simply a multiplier of y sub 0. So you're going to divide it right off the y sub 0, which stands for the initial population. Just divide this off and take this left side and do the same. Divide by the same number. 2.953, on and on and on. Let me move this down. So initial population is 19,998, what I'm pointing to right here. 19,998 divided by the answer that was on this previous step in my calculator window. So I'm just going to press as my divisor, second answer, to dump that entire number right in here as the divisor. And I get, let's see, to the nearest whole number, which is what they asked you to round to again. What is the initial population to the nearest whole number? Here's all the work, and it turned out to be 6,771. That's the whole number position. Use that number to decide whether to bump it up or leave it the same. So we're bumping it up. So 6,771. Okay, now let's see what else they asked us. Okay, so that was just this. I used this to get the k value. I used this scenario to get the y sub 0 value. So now I'm on to the third question having to do with this scenario. Determine the population of the bacteria after 3 hours. Here they want the final after 3 hours, because as the time changes, the final population. What we had here was just, you know, they can give you a final population for certain parts of it, but that's just so you can find K, or so that you can find other elements in the problem that you're going to need. So now let's start fresh. Again, this is the equation that we're using, but we have more specific information now. We don't know the final population. In fact, that's what the question is in this third part. We do know the initial population because I just found that, so 6771. Then it goes times e raised up to a power of k times t. And then I also found in part 1 what the k value is. Okay, so in part 1 I found k, and then in part 2 I found the initial population. So now, knowing those two pieces of information, I can find any sort of population I want, final population, as long as I know how long they're observing for. So this is going to be k times t. Okay, so the k value was 0.02, and I actually am going to use the whole thing. I kept track of that it was actually this many digits on the calculator window. Okay, 0.02166,084,94. And then we're going to put the amount of time in here. Now, do you see that all the information they gave us from the get-go was in minutes? So therefore, this amount of time that they're giving you in this part of the problem, 3 hours, that is not compatible with the way the function was built. It needs to be in the same units as what you were originally given. So that unit of time was in minutes. 3 hours is the same thing as 180 minutes, and that's because there's 60 minutes in each hour. 60 minutes times 3 is 180 minutes. Just putting that there, not that you're going to carry it around. Okay, so here we go for the final population. It's just going to be 6771 times second function e, and then the power on e is this big long number 0.021 times 180. And I just put that for significance, so you realize why I'm not putting a 3 there and I'm putting a 180, and that's because I converted it to minutes so that these units would match the original units for the function. Okay, so here we go, putting in the power of e, 0.02166,084,94 times 180. Close that parenthesis up, and you get 334,154, because they're asking you to determine the final population and round it to the nearest whole number. So nearest whole number, that's the whole numbers position, that number right before the decimal. The number next after the decimal is strong enough to bump that up to 4. So 334154. Okay, and that's how big the population is in this third question having to do with number 4. Okay, I'm going to stop the video here, and then in the second video I will go over numbers 5, 6, and 7.